Welcome back to the Signal Lab. Today we're diving deep into 400 to 500 megahertz band, the sweet spot for urban RF traffic. In the code we just reviewed, we aren't just looking at random noise, we're tracking WMATA, rail comms, and FCC licensed public safety signal. But before the data hits our Python environment, it has to survive the physical world of electromagnetic interference. To keep our SDR from being blinded by powerful nearby transmitters, we have to employ a bit of RF black magic, known as coaxial stub. If you look to kill the switch in our code targeting 494.7125 megahertz, you'll see a digital attempt to solve a physical problem. In the field, we often use 3 to 4 inch piece of RG58 or RG8 coaxial cable as a shortened stub. The physics here is elegant. When you cut a piece of coax to exactly 1/4 of the target signal's wavelengths and short the end, it acts as a resonant trap. At that specific frequency, the stub presents a near zero impedance, effectively shunting the unwanted signal to ground before it ever reaches the SDR sensitive front end. Calculating that 3 to 4 inch length isn't guesswork, it's the direct result of the formula. Here, c is the speed of light, f is the interference frequency, Vf is the velocity factor of the cable, typically 0.66 for solid polyethylene RG58. For 494 MHz signal, the wavelength in the vacuum is roughly 23.9 inches. Applying the velocity factor and dividing by 4 gives us physical stub length of approximately 3.9 inches. This is the hardware notch filter that operates at the speed of light. Once the hardware stub has knocked down the big interference, the remaining signal enters our Python script. In our code, we use the SciPy signal IR notch function. This is the digital twin of our physical stub. While the physical cable uses phase cancellation, the digital filter uses second order IR transform function. We define a center frequency, omega, and the quality factor Q. The narrower the Q, the sharper the kill, allowing us to drop a specific interference spike without touching the WMATA data just a few kilohertz away. A critical part of our analysis in the digital attenuation or resolution bandwidth RBW of 5 kilohertz signal. When monitoring the narrow band FM in the 490 to 500 range, we must calculate the bin resolution using this formula. In our case, with 2.048 megahertz sample rate 2048 FFT bin, each pixel on your screen represents exactly 1 kilohertz of bandwidth. To properly attend to 5 kilohertz signal, we're effectively integrating the power across 5 continuous bins, ensuring the full modulation of the voice carrier is captured in our PSD calculation. The formula used in the script is where the physics of energy meets the math of precision. We square the absolute value of the FFT to get the power, then normalize it by the square of the bins count to maintain energy conservation. 1e to the negative 12 is our noise floor, a tiny constant that prevents the code from trying to calculate the logarithm of 0, which would crash the program during a momentary signal loss. In the Python code, you'll see self.notch q equals 35. This number is a ratio of the center of the frequency of the bandwidth. By the formula, a Q of 35 gives us a digital kill zone about 14 megahertz wide. If we want to be surgical, matching the 5 kilohertz bandwidth of a standard FCC narrowband signal, we need to increase our Q to nearly 100,000. This is a trade-off. A higher Q is more precise, but can introduce ringing in a digital signal if the filter coefficient becomes too aggressive. As the code runs, it performs np.roll on the waterfall data. This creates a temporary record of the physics we've discussed. Every row of the waterfall is a snapshot of 490 to 500 megahertz environment. You can see the ghosts of the hardware stub as a permanent dip in the noise floor, while the digital notch filters appear as sharp black vertical lines. This visual representation allows us to see the FC owners like Pepco, Fairfax Public Safety, WMATA pop in and out of existence in real time. Ultimately, the most robust SDR system use a layered defense. You can use 3-point-inch RG58 stub to protect the hardware from overloading, and you can use the Python IIR notch to clean up the data for the user's interface. By combining physics constraints of coaxial cable with mathematical precision of digital signal processing, we can peer into the crowded 5 kilohertz window at 494 megahertz and identify exactly who is talking. Thanks for tuning in to the Signal Lab. Keep your stubs short and your Q factors sharp. Welcome back to the Signal Lab. Today we're diving deep into